always a pleasure for me to be back in Paris. I lived here in 2004, and my mother, who's in the audience today, and I had a chance to go out last night with a very good friend of mine that I haven't seen for about 10 years, so it's a pleasure to be here. Okay, so I want to start off with a story, speaking to business school students, but I'm sure many of you know have friends who've studied the law. So my friend Andrew did not pay for his graduation picture when he graduated from Columbia University in 2009 and got stuck with this silly small picture that says proof on it. A story that I love from his tenure when he was at Columbia is that he, like Tim Urban, the blogger, is a procrastinator. So when he does his work schedule doesn't look like this, where things are distributed nicely over the corner. It looks more like this. So he was doing his final exam his first year, and it was the night before the case was due, and the task was for him to read multiple cases, understand the facts of the matter, and then make a judgment call on how a judge, when presented with this particular set of facts, would opine upon the matter. But because Andrew was at the witching hour and he didn't have a lot of time, he's like, I can't read all this stuff. But he had a tool, a study aid, to help him make his judgment. And the study aid was answers to the same question that Columbia students like himself had given over the past 20 years. So he said to himself, okay, well, we all had to take the LSAT, the entrance exam for law schools in the United States, to come into this. We should be more or less have the same intellectual capabilities to answer this question. So how about I flip this from being me, using my individual human mind to try to reason through this problem, to tapping into a database of 20,000 people's answers to the same problem and turning it into something of a statistical problem. So not understanding exactly what the legal questions at hand were, but looking at the trends over a normal distribution, a bell curve, and saying, okay, 60% of the answers seem to fall into this category, and those are the ones that were labeled with an A. They got an A on the answer, so I'll just pick that. So did he cheat? Or did he transform a reasoning problem into a data problem? Did he make this an AI answer? As Bruno mentioned, these technologies are applying mathematics to mimic what we have traditionally considered cognitive abilities. And they challenge us because it looks like cheating, right? We don't feel as if there's any knowledge here. Andrew has exhibited know-how without knowledge. And I won't talk about that today, but I will put it out there as a leitmotif as we think about some of the social implications of these technologies. So if the AI instinct is to see a reasoning problem as a data problem, how does AI work and what is it? So I really like this quotation from Jonathan Zunger, a former engineer at Google, who says that AI shines in problems where the goals are understood but the means aren't. So traditional computer programming software, right? Engineers come in and they develop systems that use rules, if this, then that, to automate some sort of process. There's certain types of problems where there's just too many rules to write out by hand. So for example, in 1952, Arthur Samuel, who was working at IBM at the time, on a computer that used to look like that, right? They're not as sleek as they are today in our nice mobile devices. Arthur Samuel came in and he wanted to automate the game of checkers to demonstrate what a machine learning problem would look like. The history of AI and games are, they're not incidental choices. Number one, games tend to have very well-defined goals. There's an object to checkers, there's an object to chess. And you and I, two humans, can agree what we're trying to do here. And it doesn't change over time, it's always the same goal. So Samuel came in and he said, well, if we were to write out all of the rules using a standard deterministic computer programming process, there would be 500 billion possible permutations. It's a big number. It would take like 45 years for a computer to execute all of those operations to figure out what to do next. So he said, I have to change the problem. Instead, I'll just state the outcome and let the system use some back-end technology to figure out how to improve its performance against that outcome. So I won't write out all the rules, I'll let it learn through experience. In 2016, some engineers from DeepMind, now acquired by Google, applied a similar philosophy to the game of Go. To think about the difference in the degrees of difficulty for that problem, checkers has 500 billion combinations. Go has 10 to the 147 combinations, which is like a quadrillion, right? So it would take hundreds of years for a computer program to execute all of those possibilities. We can't write out the rules by hand. We have to learn from data. We have to change knowledge for know-how. But if we don't write out the rules, how do we make smart systems? So Bruno mentioned in his introduction this importance of data, right, and companies getting their data act together in order to succeed with AI. And at my last company, Fast Forward Labs, my colleague Hilary Mason came up with what I like to call the Maslow's hierarchy of data science capabilities. So at the bottom is the jargon, this 2018 is the year of AI, 2013 we used to talk about big data. And everybody's like, right, what's the difference between these two? So big data, if you take it seriously, is quite boring. It's the ability to store, collect, and process data at scale, cheaply. And that's a big deal. It used to be pretty expensive. We could fit stuff into CSVs and Excel spreadsheets, and now we have these huge Hadoop clusters that collect everything and anything. IoT sensor data, speech, text, images, you name it, we put it in there. And then we do stuff with it. And we do stuff with varying degrees of complexity, but it's all just math, right? So the first thing we do is analytics. We count, add, subtract, multiply, and divide. And if we count things from the past, like how many people liked a particular Twitter post, let's say, we can use that information to make better decisions in the future. But it's us making the decisions, not the system. When we get to data science, we move from sort of middle school math, so counting, to high school math. Let's say regression algorithms, so something like y equals mx plus b. And m, if you think about it, m's the slope. The more data you have, your slope will change. So if you're trying to do in a system that says, I live in Toronto, everybody's talking about how the real estate market is going up, right? I lived in New York before going to Toronto, and San Francisco before that. So for me, Toronto's super cheap. But all the Torontonians are complaining about the real estate market. So they might want to predict, how much is my house going to be in a year from now? And they look through the data and they say, well, what matters? Is it the size? Is it the location? What are the features of my apartment that are useful for making a prediction about how much it will cost in a year? And they might say, all right, it's the size. And then they map a bunch of data points, size on the x-axis, cost on the y-axis. And the more data they get, that slope will change. We call that data science. Note the difference with analytics. If we built out this function, input, output, the computer can make the guess automatically as opposed to our having to come in. When we get to machine learning and deep learning, basically we go from our measly world of 2 dimensions, so we humans, right, we see in 3 and 4 dimensions, 3 add 4th dimension of time. Deep learning sees in 50 million dimensions. So it's fundamentally just, you got mx plus b, and the slope moves, except the curve can look like this, and it can be, in more dimensions than our minds can consume. So if we think about that housing problem, when we do data science, we can only focus on the size, one variable in our math models. When we do deep learning, we get to focus on as much as we want. And we just throw it in the pot, and we let the systems figure out. It could be size, it could be location, it could be it has a washer and dryer, it could be this, it could be that. And they factor together all those different features with different levels of importance to make a good guess. And that's AI. Except that we think AI is more than that, right? So my definition is it's whatever computers can't do until they can. There's a sliding scale of capabilities here. And for us right now, Google Maps, a great AI application, we view as just plain old technology. It's probably the most sophisticated machine learning product that exists today. Self-driving cars we view as AI because they're on the horizon of possibility. Telemetry and telepathy and our ability to read minds, if we're Elon Musk, we think that's AI. If the rest of us, we think that's science fiction. So it's sort of more of a psychological phenomenon than it is an applied math problem, which is what it is for technologists. But it does cool stuff. So I really like Jeff Bezos's description of the fundamental impact that applied mathematics, artificial intelligence can have in companies. And he's noted, again, going back to rules versus learning, that in the past, technology helped us automate processes where it was very easy for us to define if this, then that. And now we can automate processes where it's much harder and much fuzzier to make those kind of mappings. So for example, we can do image classification. We can put in images into a system, and without needing metadata, without needing a tag, that system can say this is a cat, or this is a dog, or this is a glass of wine. And it does it because it's transformed a rules problem, a human coming in, putting in that label, which we do need to sort of get the system learning, but into a probability problem where it says on a curve what percentage of likelihood is it that this is a cat? And if the percentage is above a certain threshold, we say yes. If it's below, we say no. This is changing how we work with language. So in the past, we used to think about language the way we humans do. So we'd break apart sentences into a subject, Kathryn. Kathryn walks to the store. Kathryn, the verb is walking, going somewhere, direct object. And we would try to make the sentences make sense for the computer by breaking it down into grammatical parts. And that got us certain ways, but it was very rigid, right? We couldn't do a lot of stuff. But when we transform language into a math problem, and again, with deep learning, we can pay attention to all sorts of aspects of that language. All we do is we map it into a mathematical space, and then we use geometry as a proxy for meaning. So for example, if we want to say an analogy, as man is to woman, so king is to what? What a deep learning system will do is plot man to woman in space, plot king, and then say to the system, find me the vector, the mathematical line in space that is the same distance as man is to woman. And it will do that computation and say queen. And that's analogical reasoning in the mind of an AI. This is changing how we think about information security. So in the past, companies like Symantec or McAfee, which are the big security vendors, required a sacrificial lamb in order to identify the bad guy. So a hacker would come in, develop a piece of malware. That malware would get inside of INSEAD systems and leave a trace. And the Symantec, forensic investigators would come and they'd find that malware and they would update the code base so that any other company now had the footprint of that bad guy. What companies like Cylance are doing are flipping that around so that they can say, can I predict, what are the features, what are the characteristics of a bad guy? And then if they notice that there's a piece of code that comes in that looks just about like it, they'll quarantine it off so that you don't have to wait for the sacrificial lamb in order to update your code base. Deterministic, if then, probabilistic, guesses according to a goal. That's transformative if you think about the business value. Okay, so very brief introduction. There's obviously a lot more that one could say about all these technologies, but the key thing that I wanted to get across is that we're moving from having to write out the rules to making guesses about what something might be using complex mathematics. So what does this mean for you, right? When I presume there might be a couple of you in the audience who have aspirations to go learn Python and be writing out these models yourselves, and then there'll be many of you who aren't going to be doing that. You're going to be working with people who do that. So the question is what should you be thinking about? So what I wanted to do for the rest of the talk is walk you through what it looks like to build one of these products in a business and show you the types of questions you're going to be asking, either if you're in the business role, or you're in the sort of risk and compliance or privacy role, or you're in the sort of analyst and developer role. So all machine learning systems tend to look kind of like the following. There are variations, but this is a decent rule of thumb. So in the bottom you have the world. That world could be a website. That world could be a database with banking transactions. It's a data source, right? It's some input. You perceive things, which is basically you collect data from that world. You process that data. So let's go back to our example of real estate predictors. You got to figure out what matters. If you're in a classical machine learning world, the data scientist figures that out. If you're in deep learning, the computer figures that out. Then you put it into a model. That's the AI bit. It is overhyped. It's only a small part of what is a much larger and complicated computer programming development paradigm. So then you put it in and the model processes that data. It says, should I pay attention to this? Should I pay attention to that? And it makes an output. You got to do something with that output. It's not meaningful on its own. And actually a lot of AI companies fail. And let's say traditional enterprise efforts to adopt AI fail because they go the first part and they build that output, but they don't do anything with it. So you got to do something with it, and then you can learn once you've taken that action. So I won't go through all of this because I'm going to talk through it. There's a process that you do, every company does when they build out these systems, that involves a lot of the systems development methodology that I'm sure you've learned in business school and thinking about how to apply technology. There's a new phase because you have to deal with that AI bit, but the rest of it is not dissimilar. So let's walk through a case. So first thing you have to do is figure out what business problem you're solving. You don't just apply AI anywhere, right? There's a lot of hammers looking for nails in this space. The projects that really succeed start with figuring out, like, what's the business value of this application? So my company, we worked with a online insurance aggregator, a little bit like Expedia, but they aggregate together various insurance products. And their problem was that they had a high drop-off rate. People would come to their website, they'd scroll around, but they wouldn't actually buy the product that they were looking for. So they wanted to do something to incentivize these people to, like, take that action, but they didn't want to be spending money on everyone. Incentives are expensive. They didn't want to spend $50 and increase their cost of acquisition for a given customer by that much if that $50 was going to go to waste and people were just going to not convert. So they came to us and they said, can you help us optimize where we spend our money so that we're getting more customers, we're solving this funnel problem, but we're not wasting the money across all the customers? So we said, sure. What does that look like? So the first thing we had to do is we said, all right, let's just analyze the data. Let's see how people are behaving. And we found in our nice little bell curve, one of the rules in AI, if you're in physics, the answer is normally 0. You know what I mean? So if you don't know the answer, you're like, oh, it's 0. If you're in artificial intelligence, if you don't know what the data looks like, it's a bell curve. Like we call them Gaussian distributions. Gaussian is fancy AI speak for bell curve. So all things are a bell curve. So we come in and we say, well, let's look at how likely people are based upon their behavior, the kind of activities that they're taking. And we noticed that on our bell curve, we had on the one hand people who were super likely to convert. So we're like, don't waste money on them. They're going anyway. We had people like myself who were like, don't send me advertisements. I hate them. And no matter what you do, they're not going to convert. And then we had this nice little middle distribution. And we're like, we like them. They're the sweet spot. Because they're kind of on the fence, but if we do something, it might actually change their actions. So we found this. But then we had to do something with it, right? We made a prediction, likelihood that somebody would take an action. And then we had to find a rule that said, where in that bell curve are we going to offer something and where not? So we had to take this math model and turn it into, provide an incentive, don't provide an incentive. And then we built out our goal. So the goal for us was to get people from this website into one of the partner programs. I bring this up because note the subtleties here. We were optimizing when we figured out this math, this bell curve, to get people to phase 1. But the actual long-term value were the people who, once they got sent to this other insurance provider, actually bought something. We did not have visibility in our system into that final purchasing action. And there could be some people who transfer over but don't actually purchase, right? So it was really important for us. AI, got to know the goal, don't know the means. You have to be hyper specific about understanding exactly what your goal is. Because you might optimize for number 1 when you really want number 2, and the discrepancy between the two could be almost like a ship. Like Christopher Columbus thought he was going to India, and he ended up in Latin America, right? So if a ship is pointed a little bit differently, it can go in really different directions. Ethical pitfalls also exist between these gaps. So really important for a business analyst working together with a technologist to get this thing down crystal clear. So once that's designed, we got our optimization problem, get as many people as possible to get to X action, focus on the middle of the distribution because that makes sense economically. We got to get some data. So one of the first questions you need to think through is like, where is this data coming from and where could there be sources of bad quality? So this company has a website, people come in, there's certain types of questions that they can answer that are easy. What's your name? What's your birthday? What's your social security number, et cetera. There's others that are hard. So they might know their car make, but this website had all these questions related to like arcane, super specific insurance information. And as a regular, just plain old person, you're not going to know that. You're not going to want to take the time to do that, which means the data quality might suffer. You need to work together with a subject matter expert. So we assume that PhDs who know a lot about math could come in, look at the data, and then they do magic. That more or less always fails. The best way to understand a data set is to work together with somebody who's been working on this data for a long time. They can jumpstart what the scientist pays attention to so that as they're designing their algorithms, they're picking up the stuff that really matters. You have to be careful about tricks in data that might be proxies for sensitive features. So in Europe, with the new general data protection regulations that have come out, there's a lot of focus on profiling. So using data to try to infer who somebody might be so you can do predictions like this. And this is an example of the map of Chicago, where we might say we don't want to in any way prejudice or include somebody's ethnicity within our models. We don't want to be making judgments on who should get insurance based upon somebody's race. So we say, okay, let's just remove that column from our database. But if we do that, there can be hidden proxies. So Chicago is a very segregated place. White people live where it's pink, black people live where it's blue, and therefore, if you were to leave zip code in your data set, but remove ethnicity, you're effectively encoding for race. I've lived in Paris, I know it's quite similar here. So that's something that needs to be thought about from the ethics and risk perspective as you're working with your data. Another thing that you need to think through is, does the model need to be explainable? Does it matter if we as humans can say, why did this happen, right? So the algorithms are gonna go through, they'll find these features that matter and weight them. When you're using a deep neural network, it's impossible for you to say exactly why it made the output that it did. So there's a choice that needs to be made, and it's a business choice, where you have to come in and you have to say, do we have to go for a simpler model that we can explain more because we need to be able to explain it to our customers, or can we go for the big guns, right? In our case, it didn't matter much. We weren't making decisions as to whether or not somebody got an insurance product. We made a decision as to, once they've been cleared, who do we focus on? So less requirements for explainability than somewhere else. Finally, you put the model into production. So you've built it out, you've designed your system, you've built out this thing, and then you have to decide, all right, what do we do with it? So the first thing is, the outputs have to go somewhere, right? You gotta do something with those guesses. That will require collaboration with a creative team to build out new website features that can actually change and personalize how a website might behave based upon the predictions. You gotta be able to evaluate if it's working. So here, this is applying some science. You have to build out a test set, a control set, and convince a company that this AI thing has value above the baseline performance, right? There's business as usual, there's business plus AI. It's very important to convince somebody that business plus AI is actually worthwhile. And there's a lot of work that goes into designing the methodology to make that case. And then you gotta figure out how smart this thing should be. So you're just gonna sort of build out a guess and put it into the world and let it sit there? Or do you wanna update it once a month, once every 2 months, once a week, once a day, every hour, in real time? The choices business case here might be limited by the company's infrastructure on how frequently you update, has a big impact on how you build the system. And it's something that needs to be thought about in advance and is a mixture between a business decision and a technical capability. So just to sum this up, going back to our model of how these things look, somebody comes to a website, you push it down, the AI part occurs, right? We make a guess how likely that person is to convert. It does something in the world, a person does something, we get the feedback signal in, make the system smarter, and then we report so that the business sees that there's value. Note where AI sits. It's right there, that's it, step 3. AI is in context. It's very, very infrequently a whole product solution. So there's a lot more to this than we hear about. And the hero story for you guys is that you have to have stakeholders from business, risk, analysts, and technology and data science throughout the process. So your work should start not in the bookends, but like you should be there throughout. Okay, so final thought. So how are businesses gonna evolve in this brave new world? So what I've seen, there's sort of 2 phases here. Phase 1 of AI adoption is that this technology is put into a business to make an existing process better. So what you just saw with the example with the insurance company, we're taking something, same product, offering the best insurance deal to a customer, and we're making it smarter. We're optimizing it so that it's more cost effective. But the real magic starts when this product and process value flips to become a data collection mechanism. So I'll give you an example. My mom, I said, is in the audience today. Her company is a Wi-Fi aggregator. And for a long time, they've provided a product to people where when you go around a city, you're seamlessly connected to all sorts of Wi-Fi networks. And that was the product. They're flipping this using AI to have that AI device network, have that Wi-Fi device network be an opportunity to collect data about where people go and what they're interested in. And therefore, what started off, right, collecting data to optimize the use of this network has completely flipped its value and become a guarantor of insight into people's behaviors. We see that at Google, we see that at Facebook, we see that at all the big companies. So this is sort of the big shift. As businesses adopt AI, they will improve their processes, and then they will become potentially whole new businesses as they garner new data assets. So the best way to learn this is to do it. Don't read about it in a textbook. Go into your company, find a small project, and collaborate with people and learn. Thanks.
Thank you very much. We have time for a quick question. I'd remind you, a question, as my colleague Helma Schulte likes to say, is a single sentence ending with a question mark. Does someone have one of these magical things, a question? In the middle, let's get that man. Or yell it out.
What is Integrate.ai?
Oh yeah, so tell, what is, there you go, look at that.
Right on.
Did you plant him in the audience? Yeah, Integrate.ai, what's your company?
Yeah, I tend not to talk about what I do. So Integrate.ai, it's a Toronto-based startup. We were founded about 1.5 years ago. And we are basically a new kind of data marketplace. So we work with large consumer companies, banks, retailers, insurance companies, et cetera. We help them do that stuff. So that example I just walked you through, that comes from my work. And that's step one. But then again, phase two is that we are enabling a place where two companies can exchange not their data, but they exchange the learnings that are meaningful for customer behavior. So we're building out a big international AI insight network for businesses to exchange. It's a really interesting and dicey problem because it challenges businesses' current understanding that data is the new oil, and it is stuff that they need to feverishly protect. It's their competitive edge. We want to challenge that principle and develop a form of data sharing that sort of gets a little bit to the heart of the capitalistic value of data.
I mean, one of the things you should be making sense of is all this stuff hits in this ecosystem. Obviously, you have these big companies trying to adapt. You have big tech doing all sorts of stuff. And then you have a whole set of startups looking for places to fill gaps and do some great things. One more question. It's got to be super short, almost like yes or no. Anyone? Everyone? This was like demystifying, clarifying AI. It's all clear now? No one wants to admit that they have any questions. Thank you, Kathryn.